Okay. This is the last thing that we had last time. This is a really nifty theorem, because what it tells you is if you have a fusion one and yes ideal, then I is maximal. Probably the ideal is equivalent to the quotient ring being a field. The ideal being prime is equivalent to the quotient ring being an integral domain. And I is radical if and only if R mod I is reduced, and reduced, let me remind you, means that there are no non-zero niltons. I encourage you to prove this for yourself, because the proof is very similar. I'm gonna prove one of them, and I think the analog is similar. Let's do one. Suppose and our burden is we want to show that R mod I is a field. Okay. R mod I, of course, is a ring. We've already done this. And in fact, since R is a commutative ring with identity, R mod I is a commutative ring with identity. We want to show this animal is a field. And what does it take to show that something's a field? Any element that's not zero must have a multiplicative. Right, agree with that? So need to show the non-zero element as multiplicative. So let's let A plus I in R mod I be a non-zero element. So what does this mean about A? If I'm telling you that this is not the zero coset, what do you know about A? Not an I. It's not an I. Because in fact, A plus I is a zero coset if and only if A is an I. Okay. So A is an element of the ring that's not an I. What do I mean by this notation here? This is the smallest ideal that contains I and A, or it's the ideal generated by the ideal I plus A. So everything in here can be written in form alpha plus R A, where alpha is in I and A is in, I'm sorry, and R is in R. So it's something in I plus a multiple of A. It's easy to show that this is an ideal, and this is in fact the smallest ideal that contains all of I and also beyond that. And this containment must be strict, because A lives here and by assumption does not live here, correct? Now, what do we know about the ideal I? It's maximal. So if I comma A is strictly bigger than I, what must be true of I comma A? It has to be the whole ring. Right? Because there is no proper ideal that's bigger than I. So this has to blow up to the whole ring. And what do we know lives in the ring? Right? There's a key element.
Units.
That's right. This is a community agreement with identity. And so for this equality, it's,
So A is an ideal.
no, A is an element. It's an element of R.
Oh, I see, that's A plus.
Yes, A plus. So this means. Do I agree with that?
Yep.
Anybody see what this does for us? Anybody tell me what the inverse of A? What the inverse of A plus I is? This equation sets up for.
Alpha plus I, R plus I. It's R plus I.
Let me get this right here. This is. R, AR plus I, this is R A plus I.
R plus I, which makes it an ideal.
What this is. One minus alpha plus I. Which is what? Because alpha was I. So A plus I is in vertical. And. R minus.
Wouldn't that be one minus alpha, not one plus, if you're saying alpha is the. So so the one minus alpha plus I equals one plus I, it'd be one minus I instead. One minus alpha plus I.
Doesn't matter, this is cosine.
Oh, so it's like a minus alpha.
Yeah, that doesn't
Okay.
Everybody okay? So there's one direction. We've shown that if I is maximal, the normal I is the field. Now the converse. Now, suppose. I think I can almost build this proof in a similar manner to what I did the other way. Suppose that I have harmonized. Uh. Uh. Okay, so here's my strategy. I know that Armada is field, and I want to show that I is maximal ideal. So here's the way I'm going to tackle this problem. I'm going to show you that if any element is not an I, if anything is not an I, then the ideal generated by I and that element blows up to the whole ring. That means that there's no ideal properly between I and R. Right? Properly. So this end. Since A is not an I. This is gonna, I think, look familiar with what we were doing before. The coset A plus I in R mod I is not equal to zero coset. And what do we know? We know that R mod I is a field. We know that A plus I is not a zero element, so it has to have an inverse, right? So I don't know much, but I do know.
It's field.
Now, I'm gonna write down, what this means. Element wise, so the coset A plus I times the coset B plus I is one plus I, right? That means that, there exists, what do we call it, now let me write up this whole mess here. I'm gonna put this equation, AB plus AY BX plus XY. Multiplying that mess out on the left side there. And so this means that and I do the proof this way, so that's fine. Notice this thing whoops, is in I. Right, because X, Y, and Z are all I. So this alphabet soup here, this is an I, this is I, this is I, this is I, so this is I, right? And this is a multiple of R. So this thing right here is in IA. There's something in the ring times A plus something in I equals 1. This implies so 1 is element A. Therefore, R, this holds for all A, and so. Okay, any questions on that? Questions on that? Okay, I'm gonna give you all a couple of definitions, and then we are going to do, y'all remember the Chinese remainder theorem?
Oh.
We're actually gonna do this in a more general set. Chinese remainder theorem works for rings, community rings by identity, in a much kind of nicer setting. Now, we'll go through a careful proof of that too. But first, a couple, definitions. I'm gonna first define the direct product, definition. I'm using some examples, at least in the finite case, it's easy to put together. So let me use something formally. Let R, I, if family rings. we define the direct product, family.
In family, like a different mathematical object than set, or are we just using it?
A collection, but I didn't wanna get into that discussion, but. Yeah, so this is just a collection of groups, it doesn't matter, the index set can be finite, countable, uncountable, whatever. you want. Uh, uh, okay. We've already done direct product of any collection of groups. And these RIs are rings, so first and foremost, they're groups. I'm just gonna take the direct product of these. So you can consider this a sequence of elements from this, more generally a net, if you like, big. And I define the multiplication, I think in the easiest way possible. So an element, so if you have a multiply. Two elements of the direct product. So two of these nets. It needs to be a new thing just like this. You just do it component wise, the easiest way possible. Certain sense. If all the rings in my family are commutative, then the direct product is commutative. If all the rings have an identity, then the direct product has the identity. Namely, the identity is the 6 by 1. Let me ask you this. If all the rings are integral domains, is the direct product an integral domain? Unfortunately, almost never. Only if the index set has cardinality 1. Right? Because, for example, this is a commutative ring, but I just multiply that coordinate wise. The identity is 1, 1. Well, Z and Z is an integral domain, right? But this thing is chock full of zero divisors. You might give me a non-trivial zero divisor. There you go. So this is full of non-zero zero divisors. So this is commutative ring identity. So if you have a direct product, bunch of commutative rings, it's commutative. Bunch of ring identity's got identity, but other things may not be concerned, like for example, this. Let all. They are the ideals are co-maximal. If now remember, the ideal I plus J is the smallest ideal of R that contains both I and J. If this blows up to the whole ring, it's what we call max. Remember what this is, it's a set of things that look like alpha plus beta, where, alpha and I, beta. So for example, um, let's see. The ideal generated by 30, so all multiples of 30, all multiples of 49, these are co-maximal. And I can give you an easy proof of this. What's the greatest common divisor of 30, 49? One, right? Because the only primes that divide this are 2, 3, and 5. The only one that divides this is 7. So there's a linear combination of this. Such that 30x plus 49y is equal to 1, which is the GCD of 13.9. We'd have to come up around a little bit of findings, I guess, right? But we can certainly find it using Euclidean algorithms, right? And that's exactly what this equation means. Whatever x is, 30x is an element of the ideal generated by 30. 49y is an element of the ideal generated by 49. Once that, so the sum of these two ideals is the whole. Any questions on that? Okay, so let's look at our old friend, the Chinese remainder theorem, but now in the setting of more general things. And this is actually a very useful theorem. CRT. So I don't want to hear about any of you people calling the legislature in the state and telling them that Brookendale is teaching CRT in this class. This means Chinese remainder theorem, okay? I'd rather not be politically crucified for this. Let I1, I2 of IK be ideals of R. Then function F on my I1 on my I2 on my IA. By the way, I haven't told you what the function is yet. But remember, the theme of this course is math course, so everything should be as easy as possible. What's the best thing I can do, right? What I want to do is my input is on, yes,
That time, is that the direct product?
it is. That's right. This is the direct product. So what I want to do is I want this to spit out a K tuple, right? I need K entries. And the first one has to be an R mod I1, the second one has to be an R mod I2, and so forth, so on. What do you think? What's the easiest thing I can do? Right. Just read this, whatever it is, make it the coset representative in every coordinate, right? That's the easiest, laziest thing that I can do. And in a certain sense, it makes the most sense, I think. Is a ring homomorphism. So this function here. With kernel. So the kernel that we will prove is in fact the intersection of these ideals that we've used in this direct product. Now, here's a bonus. If in addition, the ideals are pairwise comaximal, that's why I need to- if in addition, I sub J plus I sub L is equal to R. All J mod L. So these ideals are pairwise comax. Then the intersection is equal to product. The intersection of these ideals are actually this product. Well, let me point out to you, in general, you expect the product of the ideals to be contained in the intersection, but here you're getting equality if they're pairwise comaximal. And so we're going to prove this. But before I prove this, I want to give an application. So here's a nice application of the Chinese, among many. One of the things that you may or may not be familiar with is doing silly arithmetic in ZMod n. It's actually very important in a lot of modern computer science and coding theory, cryptography, right? And so understanding the structure of these rings, these finite rings, is incredibly important in a lot of applications. So I might ask the following question. And I believe this was on the final exam from last time I taught. Here's my question. Let me say, I don't need to talk this. Although finding
You
it,
said units twice.
that's what it did. Let's see. Okay, how would we do this? Well, the ideal 400C, since it's a principal ideal, it's fairly, I want to break this down into prime power multiples, right? So let's see, I guess You got a 4 and 1 4, so that's what, 16 times 25? Look right to you guys.
Yep.
Now, the Chinese remainder theorem says that all R mod, in this case, K is 2, because we've got, 2, and notice 16 and 25 are co-maximum, right, because they're relatively prime.
Yeah.
Right? So the Chinese remainder theorem says, hey, what I've got here in my application, okay, K is 2. So it says that Z mod 400Z, Z mod 16Z, 25Z is isomorphic to Z mod 16Z. Z mod 25Z. And breaking it down into these kind of powers is going to actually make our job of counting things a little bit easier. So let's let anybody, okay, so I'm gonna write an element of Z 400. I'm gonna actually write it this way as an ordered pair, one from Z mod 16, one from Z mod 25. So here are my entries, Z mod 16, Z mod 25. I claim that the ordered pair X comma Y is a nilpotent if and only if. Anybody want to give me a good projection on what I can tell if it's nilpotent?
If both X and Y, if both X and Y are.
That is correct. Everybody agree that if there's a power of X that is 0 and a power of Y that's 0, just take whatever the maximum of those two is, and that power will be 0. Agree? How about unit? X comma Y is unit if and only if. What do you want? What do you think?
X and Y are both units.
Because if you have an X inverse and then you have Y inverse, multiplying this by X inverse Y inverse gives you 1, which is the identity. Right? And conversely, if you multiply this by something that gives you 1, that forces both X and Y to have an inverse. Everybody agree with that? Now it's much easier to count. Can somebody count for me? Well, back in this ring, can you tell me something about, notice I didn't talk about zero classes. Didn't mention them specifically up to this point. Can somebody tell me what are the units in Z mod 16Z? That is correct. Everything is relatively prime to 2, right? And that's half of it. So there are 8 units in Z16, right? And everything else that's left over must be what? Well, actually, I wanted you to say something a little bit more general
Oh,
because
zero divisors.
everything else, but what you said is correct. Because in this particular case, all the zero divisors are in fact nilpotents, right? Why is that? Because the zero divisors have at least one factor of 2 in it, right? And when you take that to the 4th power, what are you gonna get? Factor of 16 in there, so it's gonna be 0. Do I agree with that? So this is 8 units, 8 zero divisors. And they're all nilpotent. How about Z25? And you'll forgive me if I don't write these all out, but how many units are there? Or how about how many zero divisors? Actually, counting zero divisors here might be a little bit easier. How many zero divisors are there in Z25? Let's use our finger, shall we? 0, 5, 10, 15, 20. So it's 5. 5. Everybody agree? Because a zero in Z25, your zero divisor, if and only if you have a factor of 5, right? 0, 5, 10, 15, 20. There you go. Put 5 of them. And they're all nilpotent again. So how many units are there?
20.
Correct, whatever's left over. So in Z400, which is isomorphic to Z16 cross Z25, how many units do we have?
We have, we have 20 units, so they want 160 units.
I agree with that. Because to be a unit, you have to be a unit both coordinates. You got 8 choices here, 20 here. Agree? How many nilpotents? Should be 40. Again, to be a nilpotent, you gotta be a nilpotent in both coordinates, right? So you've got, what do we got? In the first coordinate, we've got 8 choices. Second, we've got 5, so we got 4. How many zero divisors? And I'll tell you, whatever this number is, should be bigger than 40, otherwise it's trouble.
200.
No. No. Oh, I know, I know where you got 200. When I ask for zero divisors, I'm talking about all zero divisors.
240.
There are 240 zero divisors. Where did you get that?
Oh, it's gonna be 200, basically like that. Basically, that's not gonna be.
You're going the wrong way on where I'm going with this. So where'd you get to? That's right. Everything's either a unit or zero divisors. So you know you got 160, that leaves 240. Right? And what he did when he first said 200 is he subtracted off the nilpotents. So his 200 that he said are all the zero divisors that are not nilpotent. Everybody okay with that? This beats the tar out of writing 0 bar up through 399 bar and going and picking through it, right? And so the Chinese remainder theorem, and the bigger I make that number, the more useful it is, as a matter of fact. So, okay, any questions on this?
So we're not, units, it's just like whichever is the first, not one divisor. Or the first divisor of 16 and 25 are like 2 and 5, other than 1.
Right, right. So this is why the prime power order was especially useful here, because the only prime that divides, the order of this is two, right? And so that gives you a nice characterization on everything that's a zero divisor, and you get a bonus since it's prime power is all these are zero divisors for your bonus.
If you were working in like 600 Z, you have like a third ring of like 3Z.
Yeah, so let's see, you'd have three, and then you got 200, so you break that down in whatever the prime power. I guess that would be what 653 times, what 2 cubed times 5 cubed or something like that. So you get different answers, but it's the same technique.
But you'd have 3 rings instead.
You have 3 rings instead of just 2. That's right. Okay, so let's go through the proof of Chinese remainder theorem. Or at least get started with it. Uh, we've already seen that this is actually a homomorphism, groups. And it's fairly easy to see that it's homomorphism of rings. F of R prime is R prime plus I, one of the R prime plus I K is equal to R plus I one, R plus I K times R prime plus I one, R prime plus I K equals F R F R prime. So this is a homomorphism of rings. That's not an issue. And what else do we say? We said that the kernel was the intersection of those ideals. So let's check that. Our claim, see where we're at. The kernel F is equal to I1 intersect, or the intersection of all the ideals. This containment. If X is in the kernel F, then F of X, which is this thing, is equal to therefore, for all I between 1 and K, X is an iso I. Right? For example, for this to be 0 plus I1, that means X is an I1 all the way up here, the X has to be an IK. Therefore, so the kernel of F is contained in that intersection. On the other hand, so this thing, yep. Then for all I 1K, X is in I spy. So X plus I spy, 0 plus I spy. So X is in kernel of that. So we got that. So we've got the kernel taken care of. Now, second statement, we're going to, go by induction. Um, I think it's our pairwise comaxial. Then R mod I one, so I see more things in R mod I one. Now, let me make a remark here. I'm going to go by induction on K. And I'm gonna look at two base cases. First one doesn't even look at. In the case that K equals one, this is obvious. It's not, because this equation reads R mod I is less than R mod I, right? So that's silly. The case for two ideals is really the heavy lifting. This is one of those proofs where the base case is a heavy work and the general case follows readily from this. So for convenience of notation, we show if I plus J is equal to R, that is I and J are comaximal, then R mod IJ is isomorphic to R mod I, R mod I. And like I said, this is the heavy lifting case. Okay, claim one,
Does that work on its own?
what?
If you're showing it pairwise, then it follows for the whole thing.
Well, there's something to do, but it's the inductive step is very easy once you have the two case. Because what happens in the inductive step is you'll appeal back to this case. So claim one. I claim that the product and the intersection are the same when it's comax. That's important. This is a homework problem that you're doing. IJ product is always contained in the intersection. Why do you get it the other way? Well, for the other containment, since there exists X and I, Y and J, such that X plus Y is equal to 1. Multiply this equation by A. Now notice that AX and AY are in IJ. Because X is in I and A is in J, and Y is in J and A is in I, right? So these products here are in IJ. Therefore, A is in IJ. So I intersect J, A is in IJ. So I intersect J is equal to I. Product is always contained in the intersection, but in the comaximal case, you get the other containment. Okay, any questions? Okay, Right. So. Here's the end game. And we'll finish this up next time, so I don't have to finish like that. If you consider. See if you can figure this out before we get back to this next time. I claim that this function here is on. This is not readily apparent because notice. I had two coordinates to fill, right? I've got to come up with anything in R mod I, anything in R mod J to make this onto, but I've only got one parameter. R goes to this goes to this goes. How could this fill every? But it does, and it's because I plus J is R. Those are co-lines. See if you can figure that out. Otherwise, we will dig that up next time. Any
Maybe that
questions?
questions are very, very interesting.
All right, we will see you all next.